Okay, it is time to do the multiple choice section of the 2017 A-Level Paper 1 from AQA for physics. So, an atom of nitrogen 16 gains 3 electrons. What is the specific charge of the ion? Well, the specific charge is going to be 3 times 1.6 divided by the 16 times the mass of protons or neutrons, mass of nucleons. So, and it'll all end up being negative. So the excess charge is 3 times 1.6 times 10 to the negative 19. Okay, and that all is going to be divided by 16 times 1.67 times 10 to the negative 27. One, two, three, four, five, six, seven. Sorry, 1, 2, 3, 4, 5, 6, 7. Negative 1.8 times 10 to the 7. So the specific charge is B. So beta plus decay. Remember that time flows that way in a oh man, that's really bad of me. Time flows that way in a Feynman diagram. So beta plus decay, you definitely have an up to a down, okay, because we have up, up, down becoming up, down, down, so proton to a neutron. And we have to have an electron neutrino because this is an antiparticle, so it has to be A. Okay, so a beam of light of wavelength lambda is incident on a clean metal surface and photoelectrons are emitted. The wavelength of the light is halved, but the energy incident per second is kept the same. Okay, so we have half the wavelength, so we have half the energy, so the kinetic energy must be decreased. The energy incident per second is kept the same. That means that there are more photons per second hitting, which means there are more electrons per second that can be emitted. So it's got to be B. Oh, what am I doing? Backwards. So wavelength is halved, which means higher frequency, which means more energy, so increases. And decreases because if the energy per second stays the same, that means fewer photons per second, so fewer electrons per second. Whoops. Okay. Electrons moving in a beam have the same de Broglie wavelength as protons in a separate beam moving at 2.8 times 10 to the 4. What is the speed of the electrons? So I have to think about what is de Broglie wavelength. So de Broglie wavelength is lambda equals h over mv. Okay, so these are the same. So what we're saying is that h over meve is equal to h over mp vp. So velocity of the electron, just going to rearrange a little bit. Those cancel out. It's MPVP over ME. Right. So back to my data table. So we've got 1.67 times 10 negative 24. Oops. Times 2.8 times 10 to the 4. Divided by a very, very, very small number, 9.11. 10 to the minus 31. My number's right. Oh, it's minus 27. Oops, minus 27. Minus 31. Okay. 1.67 times 10 to the minus 27 times 2.8 times 10 to the 4 divided by 9.11 times 10 to the minus 35. So 5.1 times 10 to the 7 according to my math. That's fast. It's still within the realm of possibility, but that's fast. Okay, so diagram shows energy level diagram for a hydrogen atom, an electron with an energy of 13 electron volts collides with atoms of hydrogen in their ground state. What is the number of different wavelengths that could be emitted when the atoms de-excite? So we cannot reach level 4 from that one because 13.6 minus 5.4 is less than or is more than 13, so it can't jump up there. So we could have, so we can get up to here. So we can see this, this, or this. We could also get up to level 2. So it could be this or this, and it can get up to level 1, so it can be that. 1, 2, 3, 4, 5, 6. 6 possible wavelengths of light. Okay, so the graph shows how vertical height of traveling wave varies with distance along the path of the wave. What is the period of the wave? So peak to peak distance is 2 centimeters. C equals lambda f. So f is equal to c over lambda, so period is lambda over t. Lambda over c, I should say. So 2 divided by 20 is 0.1 seconds. Okay, the mark scheme says C. That's not right. It has to be 0.1 seconds. It's moving 20 centimeters every second. The wavelength is very much... Why did I say 2? That's 4. Ugh, okay. Lambda is 4, C is 20. 4 divided by 20 is 0.2. B. Alright, now that's right, yes. Sorry. Okay, 14. Let's see what is not correct for ultrasound. Both can definitely be refracted, they're both waves. Both can be diffracted, they're both waves. Ultrasound cannot be polarized because it is a longitudinal wave, and only transverse waves can be polarized. Okay, so 15. Stationary wave set up. Now the stationary wave is set up on a second string wave of the same material and the same tension. Okay, so 1 over 2L square root of tension over mu. Okay, and mu is equal to mass per unit length, which is density times area. Which is 4 pi omega, times d squared. So, to get the same frequency, I have to have the same, so if I double L and I double D, it's 4D. Square root of 4D squared is 2D. So it's A. Wait, 15. C. What do we got to see? L over 2. It is T over mu, right? Where's my formula sheet? Yeah, T over mu. Yeah, density times area. Okay. So if I've got 2L in there, so then I've got 1 over 4L, and then it'll be everything else the same, 1 over the square root of so if it's 2D, that's 4D squared, 2D, oh, 1 over 8, no, that's no good. So yeah, it has to be L over 2 with 2D, and that you'll end up with things canceling out. Okay. So, okay, 16. When a monochromatic light source is incident on 2 slits at the same width, a pattern is produced. One slit is covered with opaque black paper. What is the effect of covering the slit? So, torn between A and C. I really feel like the central maxima is definitely wider. The outer maxima are definitely not wider. No, the intensity won't actually increase because you don't have two sources hitting it anymore. It's just one source hitting it. No, you're just going to see fewer maxima. Okay, when the light of wavelength 5 times 10 to the minus 7 is incident on a diffraction grating, the fourth order maxima observed is at an angle of 30 degrees. What's the number of lines per millimeter of diffraction grating? Okay, d sine theta is equal to n lambda so d is equal to 4 times 5.0 is 10 to the minus 7 divided by sine 30. Now that's actually the gap, so your lines per millimeter is 1 over d. So sine 30 divided by 4 times 5 times 10 to the minus 7. .5 times 10 to the 5. Lines per meter. Lines per meter. Divide by 1,000. 10 to the 2 for lines per millimeter. Read the question. Good. Okay, so a light uniform rigid bar is pivoted at its center. Force acts on the bar. Force acts on the bar as it ends and center. Which one shows a bar in equilibrium? Okay. So, well, moments aren't balanced here. Forces aren't balanced here. Wait a minute. Why did I say the moments weren't balanced in the first one? The moments are definitely balanced. Because that, and then you end up with 2. That 2 balances with that 2. 10 and 10. You are balanced. Okay, so it's A. Here the moments are balanced, but the forces aren't. Here the moments are not balanced, even though the forces are. You have a couple on C. Which row gives the features of graphs that provide the same information? The gradient of a displacement time graph. No. Gradient, because that is velocity. Gradient of a displacement time graph. Area under an acceleration time graph. That's it right there. Because acceleration times time is velocity. Displacement divided by time is velocity. This gives acceleration. This doesn't give anything. That gives meter seconds. acceleration, velocity. So yeah, it's got to be 19b. A rocket of mass of 12,000 kilograms vertically accelerates. What is the thrust of the rocket? So I saw one like this recently and screwed up because I forgot about gravity. So the thrust of the rocket. So what you have to think is your rocket, okay, has a net acceleration of 1.4, but that is caused by you've got your force thrust minus the force of gravity. Okay, so your thrust acceleration is going to be equal to your net acceleration minus, well, plus gravity. So it's got to be 1.4 plus 9.8 is 11.2 meters per second squared. So the thrust is 11.2 times 12,000. 1.3 times 10 to the 5 newtons. So yeah, I made a mistake on a previous video where I had basically the exact same question, and I forgot the fact that, well, yeah, you're accelerating against gravity. So yeah, that's the thrust of the rocket, because it has to be in excess of gravity. I think you got 1.7 times 10 to the 4 before, or something similar. Okay, so figure 21 shows the path of a projectile launched from ground level with a speed of 25 meters per second at an angle of 42 degrees. I swear I have seen this. I've seen some of these questions before now. So, well, it's probably the same question, just different numbers. Horizontal distance from the starting point of the projectile when it hits the ground. So, what you do is you break this apart. Okay, so this is 25 opposite sine 45, and this is 25 cos 45. Okay, so what you have to do is you have to figure out the time of flight, and the time is equal to, so what we have is we have a u, we can have a v, and we're just going to use our Suvat equations. So we have u, we have v, we have a, we need a t. So I'm actually going to write it as the Suvat equation. Now, two ways you can do this. You can either recognize that the amount of time it takes for it to reach the top of the arc and then hit the bottom on a level thing is going to be the same amount of time, so you can double the amount of time, or you can recognize that your velocity when you hit the ground is going to be the opposite it was when you launched it. So v equals u plus at. Okay. V is negative 25 sine 45. And then our u is 25 sine 45. Plus, this is important because I've defined down as negative 9.8 times t. Okay, so if we solve for t, okay, 2 times 25 sine 45 divided by 9.8 Okay, you notice I was able to just leave out my negatives because they will all end up canceling out. So 3.6 seconds. And our distance is going to be 3.6 times 25 cos 45. Okay. 63 meters. 45 degrees is the angle at which you will get the largest horizontal distance out of a projectile. Okay, so a car of mass 580 kilograms collides with a rear of a stationary van of mass 1,200 kilograms. Following the collision, the van moves with a velocity of 6.2 meters per second, and the car recoils in the opposite. So this is a conservation of momentum. So what we have is that 6.2 times 1,200 plus negative 1.6 times 580 is going to be equal to the momentum beforehand, which is going to be velocity times 580. So 6.2 times 1,200 plus negative 1.6 times 580, divide all that by 580, it's 11.2 meters per second. That's a standard city speed. Probably wouldn't have been a very pleasant collision. But it's about 37, 40 kilometers an hour. Let me just double check before I move on. 21 was D, 22B. Good. A ball that is dropped from rest and bounces repeatedly. Well, the only one where it's moving backwards is B, so you don't even really think about it. It's B because it has negative velocities on it. So in this case, they defined downward velocity as positive, and it's perfectly elastic. So yeah, B is our only option that makes any kind of sense. 24. A sample of wire has a Young's modulus E. Second sample of wire made from the identical material has 3 times the length and half the diameter of the first sample. What is the Young's modulus of the second sample in terms of E? Well, Young's modulus should be independent of length. Because Young's modulus is a material property, not a bulk property. Yeah, so it should just be E. Why am I even thinking about this? It doesn't matter. Young's modulus is a material property, not a bulk property. So it's a property of the material. The spring constant would be affected, yes, but not necessarily, or not the Young's modulus. unless you used a different material. Okay, so in the circuit below, potential difference across the LED is 1.8 when emitting light. Current is 20 milliamps. What's the value of R? So, alright, 1.8. Okay. 20 times 10 to the minus 3. 20 times minus 3. So, here we have a potential difference of 0.2 volts being lost, which means that we have 3 volts being lost here, because 0.2 plus 1.8. And then 3 divided by 20 times 10 to the minus 3. That didn't work out very well. $150 ohms. C. Okay, combine the resistance of n identical resistors connected in parallel R to the n. What as n increases? R decreases non-linearly as n increases. Because what you'll have, you'll have R, R over 2, R over 3, R over 4, R over 5. So on a graph, that is that. It's an inverse curve. It's not a line. Okay, 27. This table shows the resistivity, length, and cross-sectional area of wires P and Q. The resistance of wire P is R. What's the total resistance of the wires when they are connected in parallel? Oh, you're horrendous. Okay. I'm only saying it's horrendous because it is a bit of work to have to look at these. And really, you want to be able to do this quickly. So, resistivity is, so R is rho L over A. So now I've got rho over 4, so I'm going to put a 4 there. A divided by 2, so R. So RQ is equal to rho L over 2A. So it's half. So RQ equals 1/2. So it's equal to R over 2. So now we've got R, so 1 over R plus 2 over R equals 3 over R, so it's R over 3 is our final resistance B. See, you really have to have strong algebra skills for these kinds of questions. Because even like just there, I imagine I lost quite a few people with what I did. Okay, so which graph shows how the potential difference supplied V varies as we move contact C from position P to position Q. So at position P, we should have 0. Okay, and here, well, if we look, this is 5 ohms, this is 10 ohms. This can get up to 4 volts. This can get, this will always have, this can have up to 2 volts. So it's got to be C. So we go from 0 to 4 volts max. Yes, okay. Potential divider equation is how I get 2 and 4. But I just kind of did it in my head. So, 29. What is it asking me here? Resistor network. The EMF supplies 12 volts and has negligible internal resistance. Was a reading on a voltmeter connected between... Okay, so again, we kind of have to think of this as... So we're at 12 here, we're at 12 here. Okay? Here, we're going to be at 0, and we're going to be at 0. So here, 2/3 of the voltage get used up, and only 1/3 is left. So 2/3 gets used. So 8 gets used, and we're at 4 here, because we have 4 left to be used here. Here, 3/4 gets used up, so we're at 3 volts. So, because 3 volts can be used there. So the potential difference between there is 1 volt, B. Okay, 30. Am I almost done? Close. Okay, so 30. A bob of mass 0.5 kilograms suspended from the end of a piece of string and is rotating at a constant rate of 120 RPMs. What is the tension in the string at the bottom of the circle? So, tension is going to be weight plus Fc. And it's going to have the most tension, so they are definitely going to be added. So this is 0.5 plus 9.8 plus 9.8 times 9.8 plus the centripetal force is omega. I can never remember these. M omega squared R. Okay, but to go from RPMs, so to go from RPM to omega. Okay, so that's how many revolutions in 1 minute. We have to divide it by 60 to get revolutions per second. And because we need radians per second, I have to times it by 2 pi, because it's doing 2 pi radians every second with that. So 120 divided by 60 times 2 pi, and that equals 4 pi. So 0.5 plus times 9.8 plus 0.5 times 4 pi squared times 0.45. Okay, 0.5 times 9.81 plus 0.5 times 4 pi squared times 0.45, 40 newtons, D. Okay, 31. Which graph shows how kinetic energy from a simple pendulum varies with displacement from the equilibrium position? So when it's at equilibrium, it'll be moving the fastest, so it'll have the most kinetic energy, and it will follow a curve, not a, because it's v squared. So it has to be D. This graph shows how the displacement of a particle performing simple harmonic motion varies with time. Which statement is not correct? The speed of the particle is maximum at t over 4. That is true, because that's zero displacement. It'll have the most velocity. Energy of the particle is 0 at 3/4 t. The potential energy. Yes, that's true. The acceleration is maximum at t over a half. That's true, because we're at the restoring force on the particle is 0 at time t. That's false, because the restoring force will be maximum, because the acceleration is maximum. So D. And there we go. We've got it all done. Hopefully this is helpful.